Good afternoon, everyone. So, let's keep the discussion going and how do we make brave robots which are not afraid of contacts. So, so what I'm going to talk about today is that to make such robots, we need, advances in algorithms, in hardware design, and in sensing. And it's not just, advances in these individual topics, but a combination of these, which is going to really help us realize the vision of a brave robots which make use of contacts, right? So let's begin with the first thing, which is algorithms. Maybe I'll be a bit controversial over here and have a minority opinion, but I think it will spur some good discussion. Okay, so to study this question, we took this case study of in-hand reorientation. We all know that in-hand reorientation requires contact-rich dynamic manipulation where you're making and breaking contact. Because of the challenges which contacts bring in, there are many things that don't work as well as you would like it to work. For example, if you look at a lot of work in this area, what you would find is that they work either with very few objects, for example, just the object that you're seeing on the screen, right? And they do not really generalize to new objects. The reason being that if I give you a new object shape, then to know where to contact, where the contact happens and how to contact it becomes really challenging. The other thing to notice is that in all of these cases, the hand is facing upwards, right? So so when the hand is facing upwards, the problem is much simpler because you get supporting force from the hand itself. But what about the case when the hand is facing downwards, as you see on your right? In this case, you must fight gravity all the time, which makes it unstable and therefore becomes a hard manipulation problem. So what we set for ourselves was a goal that how can we perform this in-hand reorientation, but in the setting where we can work with a large number of objects, generalize to new ones, work irrespective of the orientation of the hand, if it is facing upwards or facing downwards. And then being able to do this when we are working with real world observations that we can measure without making a whole suite of cameras, something which we can actually deploy, something like using motor encoders or just an RGBD camera, right? So, let's see how we build this system. And, this was work led by Tao Chen. So, okay. So we have a current state ST, and we want to orient the object to a goal state, SG. Now, typically what we would have is a model or a simulation which tells us what is going to happen next. And one approach to find the sequence of actions is to use powerful gradient-based optimization techniques to give actions, right? But doing optimization through the model, just because we have contacts, becomes really challenging, as we have seen in many talks, and many great methods have been proposed to overcome it, right? But the stance I'm going to take over here is that this is complex, tedious, and requires human in the loop, which makes it quite slow. A dumber approach, which provides an alternative, is to simply use the model to take samples and not use it for optimization, right? So I could sample many trajectories from a model, and we could use some, gradient-free optimization methods to sample these trajectories, right? But the problem now happens is, if you're using gradient-free optimization technique, we cannot run this in real time because it's, going to require lots and lots of samples. So this is simpler because I don't have to be clever about how I construct my optimization loop, but it's really slow, right? So, what we could do is, we can amortize this and distill all these high reward trajectories into a policy, right? This is what a lot of, policy gradient methods end up doing, right? So this is data hungry. It requires a lot of data, but it's something that we can actually deploy, right? So that's the philosophy under which we are going to be working, right? So, let's try to construct this for this in-hand reorientation case. So this is the setup that we have. The state that we have is a joint position of the manipulator, the pose of the object, and the goal pose in which we want to orient the object to. And the actions we're going to be using are simply changes in joint position, we are trying to maximize the rewards, where reward is a simple function saying how far is the object posed from my goal post, and some penalty which says the actions should be small, right? And then we're going to learn a single policy across a diverse set of objects, over here 2000 plus objects. And we're going to use policy gradient algorithms like TPO to perform this training. So suppose we take this framework and march ahead. And first what I'm going to show you is the performance. So on the y-axis is success. On the x-axis is number of samples we take. As you see, we're taking billions and billions of samples. Yet the success rate over here is around 70%. Now, what do I mean by success? Is if the object is within 6 degrees of the goal orientation, right? So you might say, well, I spent so many samples that I can still do only 70%. Well, that's pretty bad, right? So, how do we go about actually improving the performance over here? So because this task is actually, contact rich, maybe what we also care about is, where is the fingertip, so that we can know if it is contacting the object or not, what is the fingertip velocity, the object velocity, the joint velocity, so on and so forth. Now, turns out that this information, is privileged in the sense it's very hard to measure directly with sensors. That even if you had position sensors, if you have some noise, the velocity estimates are going to be bad, right? But for a moment, let's assume that we have access to this information. Let's assume for now. And then we're going to train a policy with full state, which we're going to call a teacher policy. Now, this teacher policy learns from privileged information in addition to the state which we can measure directly in the real world. Now, if we measure performance of this system, it performs much better, also learns much faster, right? Now, the trouble is that we cannot really deploy this policy in the real world. So what we're going to do is we're going to distill this teacher policy to work just from the real world observation. And we're going to do this by trying to match actions. So the teacher policy is the expert, which provides actions, and the student policy, learning only from the real world observation, is going to mimic it, right? And we can use, for example, Dagger to perform this. So now let's look at what happens when we actually, deploy this policy. So first, showing some results in simulation. Over here, what you see is this hand is able to reorient the object to the goal pose that is provided. Now, this system can generalize to new objects that you provide it with. So over here, I'm showing you, some videos where these objects the system has, never seen before, and yet it can reorient them to the goal poses that are being shown. Right? Now, an obvious question which comes up is, okay, well, these results are in simulation. What do these policies actually transfer to the real world, right? So I'm going to give you just a teaser over here. So over here is the goal configuration in which we want the object to go into. And on the right, what you'll see is what the policy is doing. Right over here, the observation is, just, RGBD inputs, right? So what you see is, the hand kind of struggles with the object. It's not like a smooth motion that, you may want to get, but, it eventually, gets to the goal. It gets the job done. Turns out it's a very robust system. I have more videos later if someone is interested. Right? Now, the good thing about this framework is we can take the same, code base essentially, and then try to, apply it to locomotion. Right? So this is work led by Gabe Margolis, who is in the audience. Right? So, we have applied this framework for this, quadrupeds, jumping over gaps over here. Right? I mean, these policies can again be deployed in the real world. Here's some example, of, quadrupeds jumping over gaps indoors. And you can also use this to push the limits of agility. This is videos from the paper we presented a couple of days ago, where this, robot, broke the speed record for the highest speed on this platform. Now, these policies end up being quite robust. So we can actually take them, outside on challenging terrains. The robot is spinning over ice, it's stable. Right? So, what I have shown you is, the kind of algorithms we are going for is, do amortize inference, reduce the human burden and optimization. It can provide a scalable way to deal with contacts. Right? Now, the next part of this is, well, how do we improve the system even further, right? Right now, our hardware had no touch sensing. There was no compliance, and maybe even the finger design is suboptimal, right? It's almost like, you have taken like 3 rigid rods and you're trying to manipulate the object, not good. Now, so if we really want to use sensing in a framework, we need to collect large amounts of data. So how do we collect large amounts of data, which is tactile data? So for this, we have been developing an efficient and differentiable tactile simulation. Now these results in this paper is in submission right now, but as you can see in simulation, we are able to get the tactile force field, and we can use this for performing different tasks. Over here, this gripper is trying to pick up this rod in a way that it is horizontal. So first it finds the rod is heavy, adjusts its motion based on the tactile feedback. And then finally it finds a location where to pick it up, right? Because both the force fields on the left and the right sensor align, saying that it picked it up at the center of mass. Right now we can go to more complex geometries. For example, we can put tactile sensors on fingertips and then use them to, oops, something got skipped over here. Oh, no. So we can use them to do things like rotating a bottle cap, right? And also do things like trying to insert things. First, I'm showing you insertion based on touch sensing in simulation, but we can also do zero shot transfer to real world, where we train policies in simulation with tactile sensing, and then we are trying to transfer them onto the real system, right? So over here you're seeing some examples of the robot learning in simulation and then transferring them on the real hardware, right? So, okay, I guess in interest of time, I'm going to skip this, and maybe I'll end with the last part, which is the hardware design, being suboptimal. So, what we have been looking at is a scalable way, again, to build hardware. So what you're seeing over here are 4 example grippers that we have developed. The blue things over here are touch sensors. These are almost like gloves that you can put on the hand, right? And the way this framework works is, as following. What we have is a grammar for hand design, so that we can sample many, many different designs which are rigid, right? Now, if we look at the process, we can sample rules. And when we sample rules, you get compositions from the grammar, right? So what you see over here is, as we are sampling rules, we are getting a design that is being made, right? So over here, this sampling is being done manually by a human who is choosing, what pieces to compose, right? And once we have composed these pieces, this hardware, may not be ideally shaped. So a human can come in and change the design. The cool part is we guarantee every design is manufacturable. So anything you do, we can 3D print it, we can manufacture it, right? So once the design has been made, the next thing is to specify where we want to put touch sensors. So we choose regions for putting the touch sensors, and then because the touch sensors are knitted, you need to specify even more patches where you want sensors to be, and then all of this goes to a 3D printers for printing the design as well as printing the sensors, right? So the end result is this thing which we assemble. So we get the hand design, we get the knitted sensors. Over here, we are using these sensors. The hand is cutting the paper and it detects, the touch readings go up. So if it encounters something, which is rigid, the touch sensors stop. If something is soft, touch sensors, continue and, they cut it. Now, it's another task where, the gripper is, closing the nut screw, and at some point it detects it's, rigid enough, so it should not, screw it further, right? So now, that we have an automated way of doing design, can we co-optimize, design and control, right? This is the, the last slide I'll end with, where I'm showing you, gripper designs that we have optimized for particular tasks, right? So they have, chosen the shapes. so that they are appropriate for the tasks that you're seeing. A lot of this is joint work with Wojciech Matusik's lab and led by the student Jershu. So to end, to develop a scalable way to brave contacts, we need innovation in all these three aspects. And I've shown you some work that we have done in this. And I'll end with, we're looking for postdocs. So if you're interested in this area, please email me. And I'll stop with that.
Great, thank you. One question. Oh, in the back.
Hi, this is a great talk. Can you talk more about the sensing modality of the knitted sensor? Is the knitting a protection or is that the sensor inside?
So it's a piezoelectric knitting. So you have, fibers which go crisscross on top of each other. And when you get, pressure, you measure contact over there.